This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. So we start the discussion of the heat transfer. In the last lecture, so this is the topic that we are going to spend 2/3 of the time to study. So we before we actually get to the detailed discussion, there is a few things about the notation we are using here, which is to some of them a little bit different from that we used in the psychoanalysis part. So during the heat transfer study, to be consistent with the textbook as well as consistent with the convention commonly used, the capital letter Q, that corresponding to the energy term, which is the heat or heat transferred. So that's the energy term, that's similar to what we did before, and we're using the lowercase q for something else, for the heat transfer rate. Which is joule per second, and which is watts. Right? We said that the heat transfer is mainly about how fast the heat is being transferred, or the rate that is being transferred. Sometimes we want the rate to be faster, sometimes we want it to be slower. So for different purpose, for different cases. And then a more often term we used is a Q with a double prime. That's called heat flux. And the heat flux has a dimension of watts per meter square. So that's saying that's how much heat is transferred, how much energy is transferred per second and per unit area. So that's the term actually we more oftenly used. And the heat flux actually is the term directly related to how hot or how cold the surface that we feel. So I can give you an example. If you have a 100 watts of light bulb, so for example, that's for the old style incandescent bulb. So for those bulb, if you ever seen one, that's like a ball shape, and actually it's a yellow color and can be very hot. The surface You don't want to touch it if it's 100 watts, or even it's 30 watts. The surface is quite hot. The reason for that is that type of light generation is not very efficient. So most of energy you put in actually is released in terms of heat rather than in terms of light. So now it's being replaced by this type of fluorescence, which is more efficient, which means it's a cooler, so less energy going to heat, and more recently it's being replaced by the LED type of light, which is even cooler, even more efficient. All right, but anyway, this is still being used at some places. So for 100 watts of light bulb, if you consider the surface area, it's about 0.1 meter square. So if you consider it's 10 by 10 centimeter, right? So that will give you heat flux of 10 kilowatts per meter square. So that's pretty hot, right? And actually you don't want to touch it. In another case, if you consider, we said as a human body generates heat, and the typical heat that we generate is like 90 watts. 90 watts generated by a typical size of human body. And if we consider the surface area of a human, or basically the skin area, that's about, let me say, that's a human body, right? And a typical area you can consider is around 2 meters square. Then you can calculate the heat flux. So this one is like 45 watts per meter square. So that's our body temperature, feels like. So same amount of heat transfer rate, but just a different area, then certainly smaller area, more energy being transferred through, then you will feel the different temperature. So the temperature actually can be calculated using the conduction rate equation that we are going to introduce later. But certainly heat flux is something to understand more, can be understood in a more straightforward way. And then other than that, we have another term called Q dot. And this one is corresponding to the energy generation term. So in terms of dimension, that's watts per meter cubic. So this one is generally refers to the case that you have heat that is being generated within certain medium. For example, a certain solid, within it there is a chemical reaction or nuclear reaction happening there, and it can generate a lot of heat. So that's watts per cubic meter dimension, right? So I guess the only difference compared to what we learned before in terms of cycles, in cycle we use this lowercase q for the mass-specific heat transfer. But here we consider this one as a heat transfer rate. So no need to worry in terms of which letter it stands for or which letter to use in the exam, because the psychoanalysis and heat transfer, they will not cross over. So if you're using one letter, lowercase q, for its own purpose in each type of problem, that would be fine. There should be no confusion there. All right. So what I'm going to do next is I will quickly give you an overview in terms of what the rate equation looks like for the three mode of heat transfer. Because there will be some multi-mode heat transfer question in the next tutorial problem sheet. So there we have a quick understanding in terms what the rate equation look like for each type of heat transfer mode. Then we will discuss each mode in more detail in the later chapters. All right. So the rate equation right, the first we mentioned is conduction. Conduction, as we said, it can happen in solid and in a static fluid. And for any heat transfer to happen, you need a temperature difference, right? With temperature which delta T not equals to 0. So the simplest case or simplest schematic we can draw here would be the one we drew before. You have a T1 there and a T2 there. Let's say this is a wall. It's a solid wall. Then the heat will transfer going this way. And the rate equation we can write for the conduction case. That is proportional to the area, the amount of heat transfer rate, proportional to the area, how much area it has, and proportional to what type of material it is. So that's related to a property called thermal conductivity. And that's, let's assume it's a uniform in the medium there, and proportional to the temperature gradient, between these two sides. So that will be T1 minus T2 divided by the thickness of the wall, which is air. So this is the simplest case for the conduction. So based on that, you can see the temperature gradient. Actually, we are using a linear temperature gradient here. So this one is called Fourier's law, and we're going to discuss in a little bit more detail later on. So this K is the thermal conductivity. And that determine that is material property determined by what type of material you used to conduct this temperature difference. Right. So that's conduction. That's the rate equation that we're having there, and the second one is convection. Convection, as we said, is involving flowing fluid or moving fluid. And surface. That's a more typical case, and at different temperature. So the convection can happen in many ways, in many type of setup, but generally can be classified into two types. One is called external flow. The other is called the internal flow. So for the external flow, basically can be simplified. You have a plate or have a surface, and you have the flow coming in at a certain velocity and a certain temperature. And we are going to discuss later, which is for the convection, so the surface at Ts, right? For the convection problem, important phenomenon is called the boundary layer. So we know that when a flow approaching a surface, you will form a boundary layer from your fluid subject. But that boundary layer is also important in terms of the heat transfer or convection. So that's the thing we are going to discuss in detail later on. So that's the external flow. Or you have a pipe flow, and then the surface at a different temperature, and the boundary layer will also be formed in the pipe wall. And in that case, you will have the heat transfer happens as well. So in this case, we're using a mean temperature of the flow in order to calculate the convection problem. So for this case, what we used is a rate equation, which is called Newton's law of cooling, which is saying that the heat transfer rate, again, it's proportional to the area and proportional to something called the heat transfer coefficient, but basically considered as a constant. It's similar to the K property that we discussed for the conduction case, but except this is later on when we discuss the convection, the primary task is to figure out what is H for different condition. But for now, just consider it's a constant, or the heat transfer coefficient. And also, the convection is proportional to the temperature difference. So if we consider the Ts is higher than T infinity, that's for the external case. Or if I have internal case, that value would be the T mean for the internal case. All right. So when we study the convection, as mentioned, the primary task is to figure out what is H, because the temperature and the temperature of the surface and temperature of the flow can be figured out or either given, and the area is known. So to determine H, that's the primary task for the to study the convection. But that's the rate equation, which is also pretty straightforward. And the third mode is the radiation. Radiation, as we briefly mentioned last time, it's a fundamentally different way that the energy or heat being transferred. If you consider conduction and convection, conduction, you have a medium, right? Yeah, actually, the conduction must have the medium which has a temperature being different on the two sides. And the convection, you also have the temperature difference, and the fluid must get contact with the surface, and then the heat can be transferred. Or maybe I should draw the direction of the heat transfer rate going there, and yeah, for the conduction, I already drew the direction. So for the conduction and the convection, you need a contact surface. And that area that we included in the rate equation, that is the area where the heat actually transferred. Or you can consider for the convection case, that's the area where the fluid and the surface get contact with each other. The area is a contact surface area, that area is where the heat is being transferred. But for the for radiation, that's different. It's being transferred in a similar way as light being transferred. So in fact, that's one of the electromagnetic wave, just with a different wavelengths compared to the visible lights. So this radiation we typically refers to as thermal radiation, which is more in the infrared region, which has a wavelength longer than the visible lights, which we generally cannot see. But but that's being transferred in a similar way as light. So in other words, in order for the light to light emitted from sun to reach Earth, there is no any medium needed. There is no any contact surface involved in this process. As long as you don't have anything to block the light passage, right? The light will always transfer, whether you have air there, whether you have vacuum there, it doesn't matter. So it does not require any contact, does not require any medium in order for the radiation to be transferred. So that's the primary difference there. So that's requires no medium or contact. So in this case, if we want to calculate the radiation equation, for example, if we have a surface here, right, and we have another surface in space there. So if they have at different temperature, if this one is TS1 and TS2, as long as they can see each other, the radiation can happen. All right, it doesn't require anything to connecting them in order for this thing to happen. All right, and this can happen, and this can happen both ways. So later on, when we study the radiation, we will learn that the radiation actually, anything which with a temperature above 0 Kelvin can emit thermal radiation. So what we often dealing with radiation is a net radiation. So the hot surface always will give more energy to the cold surface. But the cold surface, as long as not at 0 Kelvin, it also will coming back with certain energy in terms of radiation. So if we want to know the net radiation between them, that's quite involved in terms of calculation. It's not only related to what's the temperature there, it's not only related to what's the area each of the surface is, it's also related to the relative position. So in space, I'm not talking about space outside the Earth, I'm just talking about they can be located in different spatial position. So this how to the two surfaces see each other, that will determine how much heat can be transferred by radiation. So I can have a surface which is like this, where the radiation will happen in a more effective way. If one is like this, then it will be much less effective, right? And there is many positions that can be possible, can be like this, and can be like this, and many ways. So how the two surfaces view each other, that's must be known in order to calculate the radiation. So in general, the radiation heat transfer, that's more complicated, but we often dealing with a quite simple case, particularly for the earlier part of this heat transfer problems. That is, consider we have a dome, a very large dome, and we have a small surface underneath this dome. So this is a special case which we can using a straightforward equation for calculation. So the special case, which is a small surface underneath a large isothermal dome. So if we say this is a TS1 and sorry, the TS, and this is a T dome. The surface certainly at a uniform temperature, and the dome is also at one temperature. All right, you can consider the dome is like a sky. The sky has an effective sky temperature. You can consider it's a dome, just cover everything on a surface. So in this case, we also need to consider that the surface is a gray surface, and just accept the definition for now. A gray surface is where its emissivity epsilon equals to the absorptivity. So alpha stands for the fraction of the energy that can be absorbed by the surface. So in anything coming into the surface, it can be absorbed by a fraction of alpha, and epsilon stands for the fraction of the energy that can be emitted by the surface relative to a black surface. All right. So for a black surface, a black body has emissivity of 1, but for all the practical surface, it has emissivity below 1. But for a gray surface, it said these two are equal, and both are smaller than 1 and greater than 0. Right? So that's just a concept for now. So if we assume these two, then we can describe the radiation for this special case as the Q radiation. All right. Again, it's proportional to the surface area. I should say that's the small surface area there, and times the epsilon, which is equals to alpha, times a constant, which is delta, and then times the temperature difference, Ts4 minus T dome, both to the power of force. So this is a constant. It's called the Stefan-Boltzmann constant, and has a value of 5.67 times 10 to the minus 8 watts per meter square per K to the fourth power. So if you have a special setup like this, and again, this is the most problem you are dealing with here, then you can just apply this equation, which is pretty straightforward. Here you have the temperature to the fourth power, which is different from the other two modes, where it's only to the first power. All right? And just because of that, you want to know that at the room temperature, heat transfer by radiation actually is quite small. But if the temperature is going up, the radiation will become more and more important. So that's something you want to be clear with. So the radiation increase geometrically with temperature. So give you an example is, if you have a 25 degrees C surface to have a heat transfer with a 0 degree C surface, right? And in this case, you can bring in the temperature there and assume it's a black body with an emissivity of 1. We can calculate the radiation flux, which is 5.76 10 to the minus 8 298 to the power of force, and 273 to the power of force, right? Again, you are using this temperature is Kelvin, do not using Celsius, right? Then you will have a number of 135 watts per meter square. If you have this same temperature difference of 25 degrees C at a much higher temperature, 1500 degrees C to 1475 degrees C, the same 25 degrees C temperature difference, this value you can also calculate, just bringing the same number, then it will become 32,000 watts per meter square. So that's how many times? It's more than 200 times. More than 200 times, yes. And just to give you an idea in terms of what the heat flux looks like. So the solar, the sun, the heat flux that the Earth received from the sun has a nearly constant value. So that value, if you calculate the maximum value, which is the sun directly hitting the equator, and that value is about 1.3 kilowatts per meter square. 1.3 kilowatts per meter square. So this value you can consider is about 30 or 20 to 30 times of sun, 20 or 30 of sun, which is directly shining to the equator. And because the many parts of the world which is not on the equator, that solar radiation typically is around 1 kilowatts. So in summer, midday at Melbourne, so that value is about 1 kilowatts per meter square. So you can consider that's quite a large number if the radiation happens at high temperature. All right, so that's basically the three rate equation corresponding to the three mode of heat transfer. A useful concept we are going to discuss next is called thermal resistance. So this is a concept which can be applied to different heat transfer mode, and the definition is similar to the electric or electrical resistance that are being defined. So if you recall the Ohm's law, Ohm's law saying that the electric resistance can be defined by the driving force of the current for the current and the current divided by the current, right? So if you consider the numerator is a driving force for the phenomenon, and the denominator is the actual rate that happens, or actual rate resulted from this driving force, right? So you can consider that as a transfer rate. That's how the electrical resistance is being defined, which is the driving force is voltage difference, right? That's driving the electron to flow. And the actual transfer rate is a current. So that's how the electrical resistance is defined. And our thermal resistance is defined in a similar way. The driving force for our problem here is any idea? Yes, temperature difference. That's the direct driving force. And the rate something related to heat transfer rate, right? So we're using the heat transfer rate, not the flux, which is just the Q there. So with that, you can calculate the heat transfer, the thermal resistance for each heat transfer mode using the rate equation we derived just now. So if you're looking at the conduction, all right, we can write the resistance for conduction. This is a driving force divided by the Q. So that would equals to L divided by the K area. That's for the conduction. And the convection, if we looking at the rate equation there, the driving force, the rate, and there should be 1 divided by that term. So that's 1 divided by the HA. Right? And for the radiation is more complicated as said. But for this special case, we can also follow this definition and just write this one. You have Ts minus T dome, temperature difference to the first order, then divided by the Q radiation. So that can be written, although that's a special case. So that's equals to A epsilon. Yep. This is a special case, right? So the concept of resistance, if you have a multiple heat transfer mode happening at one time, actually for the practical problem, that's often the case, then you can using this thermal resistance concept. In some cases they happens in series, and some cases they happen in parallel. And when they happen in combination, the total thermal resistance will be calculated in the same way as the electric resistance you calculated before. So for example, if they happen in series, then the total resistance, sorry, should say R total, that equals to just the sum of the each of the component. That's in series. In parallel, there will be 1 over equals to sum of 1 over of each component. Right. So if you have a multi-mode heat transfer, then you can just using this simple equation that you learned before with the electrical resistance to calculate the thermal resistance for the total. So what we typically dealing with, except for the theoretical study, what we typically dealing with is indeed the multi-mode heat transfer. So let's look at an example so that we have an idea. So there is a few problem in the next tutorial dealing with the multi-mode heat transfer. One example can be seen here. So this is one of the solar thermal water heater. So basically, it's a tube and water flowing through it. And when the sun is up, it will heat the tube, and then the water passing through it will be heated. Then it cannot be heated to very high temperature, but but it's enough if you for you to take a shower, or if you want to use some cold water instead of the want to use some warm water instead of the cold water, right? So for this type of problem, it's a typical multi-mode heat transfer, and we can have a look at it. So if you have the sun there, and you have a tube, which has a one side of wall and the other side of the wall, right? And you have water flowing to be heated. And outside is not necessarily static, so you will have the air, which is also flowing outside. So in this case, if we consider the heat transfer mode, right, which means we want to start our analysis. If we choose this surface, the outer surface there, as our analysis. So if this is the outer surface, and then we have the inner surface, then we have water there, we have air there. So this is certain material, which is typically is glass, that is to prevent the heat loss, and also allow the sunlight to come in. So in this case, we have the multi-mode. One would be the radiation, which is coming from the sun. It can also coming from the sky. So depending on the temperature, the net income would coming from the sun, because that's higher at a higher temperature compared to the sky. So that's the incoming at this surface, right? And this surface we also have the external convection, which is air which is flowing outside, which means it will lose some of the heat by convection to the outside. And then also on this surface, it will have a conduction from the outside wall to the inside wall. So that will be the Q conduct. So when the energy reaches the inside wall, it will be transferred to the inner water. Then there will be another convection. I should say that's the internal, and that's the external. All right. So this is a typical multi-mode heat transfer. And to solve this type of problem, the first thing we want to do is to choose subject to conduct the heat energy balance, which means we need to define either a surface or a volume. Then we apply the first law to it. So that's the very first step. And then after that, once the energy balance is being figured out, the next step is to bring in the rate equation that corresponding to the different heat transfer mode, and to calculate the problem. All right. So what I just described, that's the method to study the heat transfer problem. First, to select an object to conduct the first law analysis, then to bring in the rate equation for the calculation. So this is a equation. This is a problem. Here we do not requiring you to derive any any equation. For certain problem that you need to derive, you need to conduct energy balance first. Then that energy balance is conducted to a differential surface or differential volume. Then you need to integrate over the length or over the volume the problem is asking, then coming out with the equation, then solve that equation. All right. So what I'm showing here, that's you don't need to do that, but later on, when we have more detailed discussion, we will show you how to do those things. All right. So here, if we choose the outer surface as our control surface, so we conduct energy balance, that should be pretty straightforward. We have the Q radiation, that's the incoming, and then that should equals to outgoing energy flux or energy flow. That equals to Q convect external plus the Q conduct. So focusing on that surface, all right, focusing on that surface, this internal convection is not involved at all. On that surface, you only have the radiation coming, the external convection going, and the conduction going. All right. If you apply your control volume to the entire wall thickness, so if you maybe I should choose then you have this energy balance. You can bring in the real equation that we derived then to solve the unknowns there. And if you choose the wall or the tube wall as the control volume, then that's a different energy balance. In this case, the conduction becomes the internal process, right? We're only dealing with the process going into that volume and leaving that volume. The conduction becomes an internal process. So we have the radiation coming in to the volume and the convection external plus the convection internal. These are now the two streams that's taking away the energy there. All right, so conduction is not involved in this case. But if you conduct the energy balance on the inner wall, if you conduct energy balance on the inner wall, you will find what? If the energy is on the inner wall, what's the incoming heat flow and what's the outgoing heat flow? Incoming would be conduction. Outgoing will be the internal convection, right? So essentially, we don't miss anything. We don't forget anything. But the things are equal if you conduct the energy balance to the inner surface, right? So this is the first step, and bringing the rate equation is the next step, and after bringing the equation, if this whole thing is being derived to a differential area or differential volume, then you need to integrate it and then solve it. All right, so that's a multiple level of complexity involved. But if you understand how the process is, then that's certainly doable. Anything else? All right. Maybe I just write it. So the method the very first is to choose the control surface or volume. So this is often, we said this is important just because often if you don't tell yourself what surface or what volume I'm doing my energy balance, often you got confused. For example, if you choose the wall thickness as the control volume, do not get confused why in my equation I don't have conduction term there, right? So choose your control surface and the control volume, then stick to it. So internal process in a control volume, that doesn't matter. So stick to the control body that you choose. You need to have clear idea, clear definition of what you choose. And then conduct the energy balance. And then apply rate equations. Right? I should say we call the energy balance as the first law. Energy balance certainly is more than the first law. The most general principle actually is applied to not only energy but for all the properties that is conserved in the process. It should be written as the things coming in plus the things that are generated within the control body or control surface equals to things getting out plus the storage within your control body. So this is a general balance which applies to energy, applies to mass, applies to, if you apply the second law, Newton's second law, then you can apply the same thing. And later on, when we study the in the next subject, if we study the chemical reactions, you can apply this to the species. So the things coming plus things generated within your control body, this term often is zero unless it's problem specifically say it's not zero. Then equals to things leaving the system, leaving your control body, and if the problem is not steady, which means the control body or your medium will have a temperature increase or temperature change with respect to time, then you will have the storage term. So this one, if it's a not transient problem, it often goes to zero. All right. I think that's all for today. Let's have a detailed discussion on conduction next week.